Hi, and welcome to Pythagorean Theorem and Distance Formula Day. Fun fact to start today off, the Pythagorean Theorem, a squared plus b squared equals c squared, named after the Pythagoreans. It's found in many other cultures around the world. The Pythagoreans were it was a group of Greek cultists, actually. They had a firm belief, among other things. They followed Pythagoras. They weren't allowed to eat beans because they believed that whenever you farted, you lost a piece of your soul. So, fun fact to start today off. So, the Pythagorean theorem, a squared plus b squared equals c squared, is, you probably heard about it before, but you've got different sides. C is the hypotenuse. It is the longest side, and it is opposite the 90-degree angle. So it's on the opposite side of the triangle from the 90. So it goes whoop. That is our hypotenuse. The two other sides are the legs. And which one's A, which one's B, it doesn't matter. They're just the two that make the 90. They make 90 degrees. Oh, I can't spell make. So we're going to use this Pythagorean theorem to find missing sides of triangles. So we've got two of our sides. We've got a leg and the hypotenuse. I can tell that this is the hypotenuse because it's across from my 90 degrees. It's opposite my 90 degrees. So I always write that one first. And then it's going to equal my other two sides being squared. So those two are our legs, 4 squared and b squared. We want to figure out what that missing side is, so we got to do a little solving. So we've got 81 equals 16 plus b squared. We're going to subtract 16 from both sides. 16. So we get 65 equals b squared. And then we've got to get rid of that squared. So just like we were doing last time, to get rid of square root, we squared. To get rid of a square, you square root. Ooh, oh gosh. Woo! Woo! So much so, like, this is what we did in middle school. Keep in mind, we get plus or minus the square root of 65. But since we're dealing with this geometry, this right triangle, we're only going to use the positive case. Now, in middle school, I bet what you did not do, though, is simplify that radical. We want to do that. I want to see if there's any perfect squares I can get out of that 65. I'm going to do 65 divided by, what's the closest one? 64. How's that? Garbage. 65 divided by the next one, 7. So 49. How's that? Bad. 65 divided by the closest one, 6. 36. How's that? Bad. 65 divided by the next one, 5. So 25. I'm just squaring these numbers. Nope. 65 divided by the next one, 16. Nope. 65 divided by the next one. If you haven't guessed, we're not going to find anything. Nope, that's bad. 65 divided by the next one, 2 squared, which is 4. Nope. So the only perfect square we can divide 65 by and get a nice answer is 1. So we can't simplify that radical. It's always good to check. Wrong end. There we go. So we're just going to have our answer be b equals the square root of 65. And that's it. We can do the same thing over here with this one, but this one's has got a radical in it already. So, ooh, that sounds fun. So we've got 6 squared plus the square root of 8 squared. And that's going to equal my hypotenuse squared. I know it's the hypotenuse because it's opposite of my 90-degree angle. So that's x squared. So 6 squared, that's 36, plus the square root of 8 that gets squared. So those are inverse operations. They undo each other, and we're left with just an 8 equals x squared. Okay. So then we've got, let's see, we're going to square root, and we're going to do stuff. So we're going to square root this, and we're going to add them together. So I end up with x equals, there'll be a plus or minus, but we're just going to use the positive case, the square root of 44. I'm trying to save some space because I still have to simplify that radical. To the calculator! 44 divided by, the closest one I can get is 7 would be too big, 49. So let's use 6. So 36. No. 4 divided by, our best next one is 25. 44 divided by our next one, which is 16. 44 divided by our next one, which is 9. 44 divided by our next one, which is 4. Success. So the square root of 4, I'm just going to do that right away. It's 2. And then we've got the square root of 11. Oh, no. Well, there's a news bulletin. Heights families. Whatever. All right. Now, this next one. I want to know if this thing is a right triangle. Yes or no. A way we can test is we can see if this works in the Pythagorean theorem. If it works in the Pythagorean theorem, then it's a right triangle. If it doesn't work in the Pythagorean theorem, then it's not a right triangle. So let's see. 24 is our biggest. Since that one's our biggest, we want to put that one in the hypotenuse spot. We don't know if it's a hypotenuse because we don't know if we have 90 degrees because we don't have an angle mark there. Sure looks like 90, but it could be off by a little bit. We're going to square the other two and add them together. 24 squared, I don't know. I think it's a big number. So yeah, 24 squared is 576. Okay. And then 23 squared, what's that? 529 plus, I can do 7 squared is 49. So we get 576 equals, we'll go to the calculator, 529 plus 49. We get 578. Oh! Oh! So good. Oh, it's so close, but it's not quite there. Since they're not exactly the same, this is not a right triangle. They need to be exactly the same in order for them to be a right triangle. Since it's off by just a little bit, it's not a right triangle. If this was 576 and 576, then we would say, yes, that's totally a right triangle. But since they're not the same, it is not a right triangle. So if they're equal, then it's a right triangle. Right. Now this next one, they didn't give us a diagram, those jerks, but wait, I'm the jerk. I'm the one who made these. I'm calling myself a jerk. Oh. So all we gotta do is just draw it ourselves. So it's got 2 legs. They told me it was a right triangle. So we've got 3 and 4, and I want to know what this is. So that is our hypotenuse. So x squared. We get 3 squared plus 4 squared. We get 9 plus 16 equals x squared. We get 25 equals x squared. We square root both sides. We do get a plus or minus, but we're just going to use the positive case. And we get, ooh, a nice number, 5. So we get 3 4, and 5. Oh, look, they all turned out to be nice numbers. Like that didn't happen before. Like, see up here, we got a nasty number and we got a nasty number. Ooh, that's really cool that they're all the same. If they're all the same, they get a cool name. They're called a Pythagorean. Triple. It is three numbers who are all whole numbers that work in the Pythagorean theorem. They're pretty neat. That's it for the front side. I'm going to do a video break, and so we can hop to the back.